concept of elementary reactions finally. And hopefully that will help you connect to some of these other models here, particularly model 3. This is the interesting one, okay? The first model for a simple first order mechanism, okay? So in elementary reactions, I'll set up by saying, suppose we have the simple mechanism, okay? A reacts and forms some intermediate. And it's a stable, unstable intermediate, okay? And that reacts with rate constant Ki. Well, that intermediate is unstable. So it quickly forms the stable product, okay, at rate constant Kp. Okay? So now, if we were to add up these two reactions, it just looks like A goes to products at rate constant K, but we have no idea what the order is. So we don't know this reaction order. But for the elementary steps, we do. And the elementary steps, the reaction orders will always be the stoichiometry. But that's only true on the elementary steps, okay? And here's why we don't know what this order is. Because if, let's suppose, that both Ki and Kp have similar rates, then that means these reactions are in competition with each other. And that means we won't get a simple first order, second order, whatever for the main mechanism. However, let's suppose another condition, okay? Let's suppose this first step is very slow, okay? And this last step is very fast, which most of the time this is going to be the case in a mechanism like this, right? If this intermediate is unstable, it's not going to be formed quickly. It's going to be formed very slow. And if that intermediate is unstable, it's going to quickly decay to products, okay? So if this is the case, then the rate of this second reaction doesn't even matter, okay? So if Ki is much greater than Kp, then the reaction just looks like A goes to products with rate constant Ki, right? It's like that second reaction doesn't even matter, okay? And I won't write Ki just to avoid confusion. I'll just write K, because that is now what we would view in our experiment. If this intermediate very quickly decayed, we wouldn't even be able to detect it. So it would just look like we have a first order reaction. And the reason why it would look like we just have a first order reaction is because the rate of that very first step is Ki times A, and we know that this was a first order step, okay? If, let's say, for example, this second step was a second order or a third order or whatever, it doesn't matter. If it's extremely fast compared to this first step, then the total reaction order is just going to mirror that of the slow step. So the slow step is rate determining, okay? And so when we have these types of reaction mechanisms where there's one step that's very slow and one step that's very fast, our kinetics becomes quite easy to work out, right? We do the method of initial rates, like I showed you back in the very beginning, and that would give us the total reaction order. However, okay, if our mechanism is complicated, So if our mechanism has several steps, which most of the time that's the case for chemistry, okay, then the issue becomes now we don't get a simple reaction order, okay? We're going to have to do the whole mechanism. We're going to have to look at the kinetic time step in the mechanism, okay? And I've got another video that I recorded several years ago now that's going to get into this on the steady state approximation and consecutive elementary reactions. It's going to continue along with this. I don't want to re-record that, so it's going to be a little bit different than this format that I'm recording in now. So use all of this open space on these slides to follow along with that, okay? But what I want to show you here is when I go through that video, try to make that connection to this Model 3, because, I mean, I know I wrote A, B, and C, but it's the same mechanism. A goes to I, and then I goes to products, okay? So follow along with that. That's going to help you put these rate orders together. Obviously, I've got it up here, so you can pause this and look to make sure you get it right. But what I want to show you here on the manipulate feature of this, on this mechanism, this gets pretty cool in our simple mechanism, okay? So the first thing that I'm going to do here is turn off the rate constants, okay? And let's just put in like maybe, I don't know, something easy, like 1 molar or something like that. Okay, so there's roughly 1 molar of A. So I've turned off the rate constants, so there's no reaction. Okay, so now if I turn up K1, K1 only makes the intermediate, right? So in this reaction, A is the A, B is the intermediate, and C is the product. So if I only turn on K1, I don't make any product, I'm just making intermediate. But now watch what happens as I turn on K2. Oh, look at that. So now C is my product, okay? And now I'm going to do this, I'm going to put them like both in the middle actually, okay? Great. Look at that. So this is, I'm going to show this to you in the video, the next video. This is kind of a special point. This is in particular when the two rate constants are the same, okay? You notice the intermediate is produced but then goes away. And that owes to a maximum, a local maximum of the intermediate where the concentration of A and B are the same. That's in the limit where these two rate constants are very similar. And that's where this would get complicated to see what the overall rate law is, okay? So, but now if I turn K1 way down, watch what happens, okay? If I make K1 very slow and I make K2 really fast, this is what we call the steady state approximation, which is going to be the next video you'll see. And we call it the steady state approximation because now the intermediate B is just being produced at this steady state. And what that gives us is it looks like the reaction is just a first order decay in A and a first order production of C, right? We don't get this complicated time profile. It just looks like this thing right here, A goes to products. However, like I said, when both of these rate constants are very similar, so as I turn down K2 and I make it approach that of K1, the reaction becomes much more dynamic, right? Especially something like that, right? And definitely this region in here, that's not exponential. I know my eyeballs aren't perfect, but I can tell you through my experience that now the profile of C and A are not this simple A goes to products. The mechanism is quite dynamic, okay? So we can only look at the total reaction order and say what the order is if we can definitively say what the rate determining step is. If we can't definitively say what the rate determining step is, then we can't just simply look at a reaction and use the stoichiometry to give us the reaction order, okay? But definitely in the elementary steps, all elementary steps, the reaction order is the stoichiometry. And we have names for all of those things, okay? So a first order elementary step is called unimolecular. And it's first order because there's only one molecule. It's that simple, right? Like this. These are all simple unimolecular steps, okay? A second order reaction we call bimolecular, okay? Because two molecules are involved, right? And then finally, when we go third order and beyond, we call that termolecular. And in the coming weeks, I'm going to talk about third order reactions a lot. They're very interesting. As it turns out, reactions that are driven by heat in their fundamental mechanisms, there's almost always a termolecular step. So this is with respect to like explosions and combustions. Within the mechanism, you don't see it in the total reaction, but within the mechanism, there's almost always a third body, a termolecular body in those mechanisms. So they are not straightforward mechanisms, okay? Okay, great, folks. So watch that last and final steady state approximation video. And make sure you go through it because that's really, this steady state approximation video, there's also an example of how to do a mechanism. It's really going to be key for you getting your project off the ground and started. Okay, folks, so after that video, that'll wrap it up for this first part on kinetics. Okay, I'll see you later.